Hello, my name is Sonakshi Sharma, and I would be talking about convolutional neural networks using CIFAR dataset. I have had an opportunity to discuss about TensorFlow and get exposed to different libraries like MATLAB, like NumPy, dealing with arrays.
To begin off, I'm giving a detailed report of what I did in my project, which involved CIFAR-10 data set, which is a data set which comprises of images of 32 to 32 pixel photographs, and it has 10 classes like frogs, birds, cats, ships, etc. And the CIFAR data set was developed along with CIFAR-100 data set by the researchers of CIFAR Institute. When it came to the designing of the model, which is my first part of the project, as in we had been asked to handle two parts of the project. First one being the initial model, in which we designed the project in a different way, and then the second part of the project, which was the improved model. We possibly redesigned the model to see how the prediction capabilities are going to be increased. So in the first part of the project, where I designed the model, it was a two-blocked model. When I say two-block model, I actually mean a convolutional layer followed by a max pooling layer, and then another convolutional layer followed by another max pooling layer. I'll get into the details of the design of the project, but this was just a quick overview of what I'd done. So to begin off, I started with creating a CIFAR-10 data subdirectory under the main directory, which was the JPTR ADTA directory. And in the CIFAR-10 data directory, all these batch files, when I say batch files, I mean because the data set comprised of 60,000 images, I'm sorry, 50,000 images. And these 50,000 images were broken down into batches of 5, which were used for the training set, the 10,000 being used for the test set, making a total of 60,000. So in the first part, in all these different batch files, the 50,000 images were for the training set were bifurcated into batches of 10,000 each, which is what happened. And then finally, the test batch comprised of a set of 10,000 images. So all these files were loaded into the CIFAR-10 data directory. And then eventually, so the path of the directory was given to unload the directories, to unload the batch files into being processed into our deep learning model. A define unpickle function was used here to unload all the data files and put them for usage in the deep learning algorithm. So all these data files had been labeled using these different numbers, which were provided into an array named all data. So the first part actually dealt with looking into, or a sort of data visualization for understanding these batch files have been labeled. So when we use this key function, we came to know that there was a section of file names, there was a section of labels, and then there was data and data labels. So we could also, when I used the batch.meta file, which was one of the files present in the set of batch files. So this provided the names of all the different labels which were being used in the data set, and these were the different labels. Moving on to the visualization part of the data set, where the matplot library was used. In this library, of course, NumPy library was also used because we were using the concept of arrays here, and NumPy deals with arrays. So the first part was the important part here was the reshaping and the transposing of the images. Why it was important was because we had to make sure that these images which are being fed into the NumPy array are the images which are being fed into the convolutional layers are suitable as or are presented in a way to the CNN layers in a way in which they take the images. So basically, there were the image size was 3072, which was broken down into 32 and 32, and they were broken down into three sets. which is why every image, like the image pixels, were broken down into a set of three, where the first one was the first and the second one was the width and height, which refers to the 32 and 32. I mean, the third and fourth was the width and the height. The three were the number of channels, and finally 10,000 was the total number of images present in one batch file. Finally, when these images had to be passed on to the to matplot functions or TensorFlow functions, at that point of time, these images had to be transformed in a way that the number of channels and the width and height were presented in this sequence. So 0 actually represented the number of images present in a batch. 2 was the number of channels, as in if we look into this array, so 0, 1, and 2. So this one, 3, actually was, it was meant to be on the second number, as in the number of channels. And then finally, so after transposing, we got the images in a form which was which had to be the number of channels, the number of images, the number of channels, the width, and the height. So this is why the reshaping was needed here. We also looked into what was the maximum pixel value for each image, which was 255. This was needed eventually for the normalization of the images so that they could be fed to the convolutional layers. We also took the different images which were present, I mean, just to get an overview of how the images looked. And we could see that the images actually did not look very clear, and that was because of the low resolution of the image. Eventually, one-hot format was needed for the labels to be presented in a binary form, which is why this function was also declared. In this function, one-hot coding is needed when we present the integers in the form of binary numbers, and that is exactly what this one-hot encoder function did for us. Eventually, the CIFAR helper class was declared for different helper functions which were needed. These helper functions they were needed for different processes initiated during building, training, and testing of the model, and functions like preparing the pixel of the data for training as well as test images was created, which was this one. This part, the setup images part, this was going to prepare the pixel data. Then also a batch function was created to feed the batch of images to the session function, which was this part. This function would actually feed in present a batch of images for the session.run function. And all these helper functions were enclosed within the CIFAR helper class. The need for that was for any function to be used or accessed within this CIFAR helper class, it was very important to first initiate the class of the function, the class with an object. And in this case, we used an object named ch, which was the initiating object for this class, and that is how we could use them. Similarly, other abstract function bodies were also created, like initializing the weights for the convolutional layer, initializing the bias. There was also a creation of convolutional layer, which was this function was also created, into which the inputs and the size of the filter, the filter shape was passed in. So I would just explain as we actually execute these functions. I could tell you like what exactly would be happening here. If we look into this part, the third line present in this function, we see that the number of strides, as in how much would a particular convolutional layer move, what would be the number of steps moving when we would use the filter. So this is what strides, and padding was the same because we need the same size as the filter. That is why we kept the padding as same. If we would have kept it if we would have changed same to some other value, then we would have got a reduced size of the output, which is something we did not need. We used an activation function named relu for this, and the relu function was suitable for the convolutional layers, although we use softmax function for the fully connected layers. A max 2x2 pooling layer was also created using this function, and size of the filter would be the same for max pooling layer as it would be for the ReLU and the convolutional layer. And then another wrapper function was created for fully connected layers. There were placeholders which were also created. The placeholders took like, none was used here because we did not know the particular the number of the images which would be passed, and that's why none came here. 32 and 32 was the width and the height, and 3 were the number of channels being used because we had broken down one particular image into 3 channels. And then the same, so placeholder function is definitely needed because we need to make sure that the data type of the image being fed to the convolutional layer is appropriate, and float was needed here. That was the reason we chosen float. Now we begin off with the feeding of the layers. Here we feed it off the convolutional layer with a filter size of 33364. This was we definitely chosen. We did not choose the filter size of 5, as in 5 by 5, which was used in case of MINIS data set. Just give me a minute. I will open up the MINIS data set as well. Yes. So if we look into this one, we fed in a filter size of 5 into 5 here, but in this case, we chose a filter size of 3 into 3. Considering the image, also we chose in a 64 here. 32 was the pixel value. 32 into 32 was the pixel value for the images in this case, whereas for the MINIS data set, the pixel value was 28 into 28. And then we moved on to create the pooling value. For the ReLU function also, the filter shape was the same. And if you see, this was the input value which was passed on. So this function actually was called, like when which function we were calling? We were calling the convolutional function here, this one. And we see that there were 2 arguments. One was the input, which was the image, and then the shape, shape of the filter. And that is what was called in this case. Also the pooling layer outputs, where we use the output presented by the ReLU layer, was passed on to the pooling layer. And then again, we called on the max pool function, which was this one. We passed on the filter size, we passed on the inputs, and that is when the function was passed, the function was called. After these 2 blocks, as I mentioned, that the first design, as in the initial design, dealt with 2 blocks. So one convolutional layer, one pooling layer made 1 block, and then second convolutional layer and second pooling layer made the second block. After we get the output, as in pooling layer 2 outputs, we need to flatten the data, and this was needed because we had to feed the data into a fully into fully connected layers. And flattening the data was needed because we had to make sure that it suits the requirements of the fully connected layer, and so we had to flatten the data and convert it into a 1D vector instead of a 4-dimensional vector. So that is exactly what happened here. We flattened it, and then we after flattening it, we got this output, which was fed to the fully connected layers. If we see, we fed pooling layer 2 output flat to the fully connected layer, and then it was followed by a ReLU activation function. After this, we decided to choose in a dropout rate of 0.5. So if we see hold probability here, we will be able to see that we chose a hold probability of 0.5, which was needed because here if we see eventually, so this actually calls in for the hold probability. So yes, that was needed. The dropout, when actually the session.run was executed, that is when this this function was also executed. And then there was a prediction layer which was created. When we say prediction layer, it means that the final output layer, and we know that the output size was 10 because we had 10 labels. And finally, the softmax cross entropy loss was also calculated. This was the loss was needed to understand like how much is the prediction capability presenting in terms of the loss. Like what is the loss in the prediction capability. And then the optimizer, we used Adam optimizer. There could be other optimizers which could also be used, but optimizer seemed to be the most suitable one and very frequently used. And then eventually this is the optimizer which used a cross entropy mean. I mean, the softmax cross entropy was used here. That was a very like that's again something where which is frequently used. So we went by that process. This was like the designing of the layers process. Finally, the training began, which the first part here was to initialize the variables. We chosen 5,000 steps. Now the steps here, every single step refers to one batch being executed. So yes, we decided that the steps had to be 5,000 as per the instructions of the professor. And then so yes, this CIFAR helper class was initialized. The object of the CIFAR helper class was initialized, and then the setup images, which is what I mentioned. I could just go back and show you one more time what exactly happened. This was a class, and the function was declared below. The object was initialized. So basically, this class was activated by the declaration of the object. And then using ch.setupImages, this part of the function was executed where the images were normalized, the batch was decided, and then after the normalization of the test and the training images, they were passed on to self-test images and self-test labels, and which is so because these normalized images had to be used in the training phase, and that is why this calling of this function is very important. Also, the after running this part, the variables were initialized, and after yes, the TF session was started, so this where's initializer is actually this part, because this held the values of the initialized variables which was passed during the session.run function. So when we say variables.initialize, it initializes all the filter values, all the the width and height which was set. So that is what happened here. For I in range steps here, we passed on the steps. We made sure that the steps were 5,000, which had been initialized earlier. If we see again that this ch.nextBatch function was again called here, in which we passed in a batch of 100, as in 100 images per batch were passed on. So in every batch file there were 10,000. And we passed on, so out of every every 10,000 batches, there were so in every 10,000 images, a batch of 100 was passed. So yes, like 10 batches technically, 10 batches of 100 size each were passed. So that's how we can say it, right? So this was the batch size. So 100 images were passed in one go, and then the session.run function was executed, in which, so this next batch, if we see, this is again a part of the helper function which we had mentioned earlier, this part. If we see that we reshaped here, and then the training went on, see the batch size upon the length of images, right? So this is the whole execution, in which in the end it came out to 10 batches of 100 batch size each. So this was executed, and X and Y, like the images in the form of batches, like small batch sizes, were passed on to the session.run function, which is what happened here. The batch 0 and batch 1, this refers to the labels and the images, and then whole probability of 0.1 was chosen. Whole probability refers to the dropout rate. So basically, after the prediction, so some portion of the images would be dropped out, so that just to add to the rigor. And then we looked into because we wanted to test after every 100 steps were executed, which is why we chose this function, right? And because there were 5,000 steps, and after every 100 step, a test image was executed, like a test set prediction was executed, which means we get 50 plots of the testing accuracy. So we can see that the interesting part was that in step 0, the accuracy was on the test set was 0.1, but it hopped to a 0.416 in the next 100 step. I'd actually like to compare it and just switch between the different models here. But before that, let's just get a quick review of what exactly happened here. So first hop to the 100th hop was actually a pretty decent hop, but eventually the prediction accuracy kept increasing consistently over subsequent steps of 100 of a gap of 100 in between. So yes, we see that the accuracy for 100 was 41.6%, then it increased to 47, then 50, and then by the end the accuracy on the 4900 step was 69.84, which was a decent increase in the accuracy over the subsequent steps. If we move on to, if we compare this accuracy with the initial, with the MINIS data set, in which we went through the same procedure and we looked into the accuracy here, the jump from step 0, so in step 0 the accuracy was 0, it was 8%, right? 8.58%. Whereas on the 100th step, it came up to 94.4%, which was a major jump, which was a major hop. And then the accuracy kept increasing consistently over the steps. There were times when the accuracy actually decreased over subsequent steps, like this one. On step 600, the accuracy was 98.15%, whereas on step 700, the accuracy was 97.91%, which was a decrease, a slight decrease though, but a decrease in the accuracy. So and then on 4900 step, the accuracy came up to 98.78%, although there was a slight decrease from the 4800 step, which was 98.86%. So yes, I mean there was like a low and high in terms of accuracy. The overall the graph was consistent in terms of the accuracies for the MINIS data set in comparison to the CIFAR data set, where the accuracy was not as much higher, but it did increase consistently. We can also see that in 4700 step, the accuracy was 71.11%. In 4800, it was 71.63, whereas in 4900, it came down to 69.84. So it did show signs of overfitting and underfitting. Overfitting and underfitting actually means that, so actually overfitting would mean that the data set would perform would predict very well on the algorithm would predict very well on the training phase of the data set, whereas it would not predict as well on the testing phase of the data set. So when you use a training data set, the algorithm would predict well, whereas if you use the testing data set, the algorithm would not predict as well, as great as it would when the training data set would be used. So this is an indicator that there's been too much of training, and the data set has just been able to learn from the training data set and is not generalized enough to be used for other data sets. So it cannot give great prediction results for other data sets. Whereas underfitting, when it comes to underfitting, the model performs badly when it is both on the training as well as testing data set. So even when it is predicting for the training data set on which it has been trained, it would not predict as well. And when it would predict on the testing data set, it would still not predict very well. So that would be underfitting. So I see a problem of either overfitting or underfitting coming up in this case. Apart from that, yes, there is always a scope for improvement in the models in terms of increasing the convolutional layers or increasing the regularization techniques like dropout regularization or maybe batch normalization. So these are different regularization techniques which could be used for improving the model. So let's look into the improved model and see how the prediction accuracy actually changed for the improved model. So in this model, the same CIFAR-10 data set was used, but what was done in this case was that I used like a 4-layered model. I would just show you what exactly I mean by a 4-layered model. So here there was first one. So when a 4-block model. So when I say a 4-block model, one block actually refers to one convolutional layer followed by a pooling layer. And I also introduced regularization techniques, 2 regularization techniques. First one being batch normalization, and of course we did use dropout regularization, which was used in the previous model as well. As I mentioned, we said there was a whole probability of 1.0. A whole probability of 0.5 being used for the training set, and a whole probability of 1.0 being used for the testing set. So dropout regularization was used in this case already in the initial model, but in the final model, I used two regularization techniques. First one being dropout regularization, and the second one being the batch normalization. So in which so when it comes to batch normalization, actually the whole batch is actually it is normalized. It's let me just go through the steps here. When I say that this was a 4-step a 4-block model, so I mean that there was here. Yes. So there was a convolutional layer, there was a pooling layer, which was 1 block. Then there was, yes. So there was a convolutional layer, there was a pooling layer, and I said I introduced batch normalization. So one batch normalization was done on the output of the pooling layer. If we see this, so this was 1 block. And then the second block was the same, convolutional layer, followed by a ReLU activation, then pooling layer, another batch normalization. So that was the second block. Then the third block was convolutional layer, another pooling layer, and then another batch normalization. And then in the fourth one was another batch, which was convolutional, pooling, and batch normalization. After this, the output was flattened for it to be fed as a 1D vector to the fully connected layers, and then a good portion of again, there were like the dropout was done, which was just similar to what was done in this case, 0.5 for a dropout rate of 0.5 for the training data set, and a 1.0 for the testing data set was done. And then in this case, again, the same number of steps were followed, the same wrapper functions were used. And if we look at the accuracies here, we can see that the accuracy initially was 1%, or let's say 10%. Yeah, so 10%, and then that increased to 37.28%, which was again like a good jump in comparison to what happened in this case. This was the initial model, so it won to 41.6%. That was also a big jump. So here also the jump was not as much, 1 to 37, which was almost similar. And then the consistent increase went on from step 200, 300, 400, 500. And then in the end, the accuracy came up to 72.07%. What was also interesting here was the last 3 steps actually showed a pretty consistent accuracy of almost 70% or a bit above in comparison to the first one here, in comparison to the initial model, where it just dropped down to 69%. So I don't see much of a difference in the accuracies of the model and the initial model, where the number of blocks had actually increased like by a number of 3, but still the accuracy did not seem as much improved. So that there could be a possible reason that the data set, the training of the data set was not being done properly in terms of the problem of overfitting and underfitting, which I mentioned. That could definitely be one of the reasons. The second reason could also be the results on the data set. They might need better regularization techniques. That could also be the one. That could also be another reason. The additional layers, in the improved model, although they should have increased the chances of model not getting trapped in overfitting or underfitting, but the fact that they did not show as much improvement could be an indicator that the images being used in every batch of the data, every batch being passed, may just not be generalized enough to indicate that this to be used for any other data set in terms of prediction. So I see these problems coming up. Maybe the dropout probability could be decreased. Maybe we dropped out quite a few images which may have been better indicators of prediction of the model. So these are different factors which could come in.
Thank you so much, and looking forward to many more great experiences with deep learning.